Welcome to The Explainer. Today, we are diving deep into a really classic linear algebra exam problem. But instead of just solving it, we're going to turn it into an intellectual journey. We're going to unpack this fascinating transformation that takes pretty simple polynomials and turns them into something way more complex. So let's see how this thing works.
Okay, so here's our game plan. First, we're going to meet the polynomial machine. That's at the heart of this whole thing. Then, and this is super important, we'll test if it plays by the rules of linearity. After that, we'll map out everything it can possibly create, figure out the pieces it leaves behind, and then, finally, we'll see the beautiful, bigger picture that it all fits into.
All right, first up, let's meet the star of our show, this transformation we're calling T. You can really think of it like a machine, It has one very specific job. But what exactly does it do to the polynomials we feed into it?
So here it is, the one crucial rule. T takes any polynomial you give it, as long as its degree is 2 or less, and it finds every single x and swaps it out for the expression x squared minus x. It's a pretty simple substitution rule, but as we're about to see, this one little rule creates some really interesting and complex results.
Let's make this real with a quick example. So if we pop the simple polynomial 2x plus 1 into our machine, it just follows the rule that x becomes x squared minus x. We do a little bit of algebra to simplify, and bam! Out the other side comes 2x squared minus 2x plus 1. See? Simple input, more complex output. Now, here's the thing. For this machine to be useful in the universe of linear algebra, it absolutely has to be well-behaved. That's what mathematicians call being linear. And honestly, this is the most critical part of the entire problem. Proving linearity, that's what unlocks our ability to really analyze the structure of this thing. So what does it actually mean to be linear?
We're really just asking a pretty simple question here. If we transform a mix of two polynomials, is that the same as mixing their individual transformations? Basically, does our machine play nice with the basic rules of math, like addition and scaling? Let's find out if it passes the test. And the answer is a resounding yes. The source material shows this really elegant proof that this formula works. It holds true for any two polynomials p and q, and any scalars alpha and beta. And this is what confirms it for us. T is, in fact, a linear transformation. It's predictable, it's consistent, it's exactly what we want to see.
Okay, great. T is linear. So what? Well, that's actually a huge deal. Now that we know it's well-behaved, we can really start to investigate its impact. We're going to map out its image, which is just the fancy term for the set of every possible polynomial that T can spit out. We're trying to find the footprint it leaves on the mathematical landscape. Now, what's really cool is that to find this image, there are two beautiful paths that both lead to the exact same answer. On one hand, we could just transform a generic all-purpose polynomial. Or, and this is maybe a little more clever, we can just transform the most basic building blocks of the space, in this case just 1, x, and x squared, and see what they turn into. And it doesn't matter which path we take, the result is the same. Every single possible output from our machine is just some combination of these three specific polynomials you see right here. This set is what we call a spanning set for the image. They're like the fundamental ingredients that T uses to cook up all of its creations. So we have these three polynomials, but are they truly independent? Can any one of them be built from the other two? To check, we do something clever. We represent them as coordinate vectors, just like in this table. It's a way to strip them down to their bare essentials. Each row here is one of our output polynomials. And the rank of this matrix, which is just the number of truly independent rows, is going to tell us the dimension of our image. And there it is. The rank is 3. Now, this is a huge insight. What this means is that the footprint of our transformation, its image, is a 3-dimensional subspace. And that's pretty wild, right? Even though the outputs can be 4th-degree polynomials living in a 5-dimensional space, they are all trapped, confined to this very specific 3D slice of it. Okay, so we've just found this 3D subspace that our machine can create. But remember, it's living inside a much bigger 5D space. And that leads to a really natural next question. What about the rest of it? What's in that part of the universe that our machine just can't get to? This right here is the critical question that's going to lead us to the final piece of our puzzle. We need to find what's called the complementary subspace. We are literally hunting for the part of this mathematical universe that our transformation, T, completely misses. And the source material gives us this brilliantly simple visual solution. We take the matrix that represents our 3D image space, and we just ask, what are the simplest vectors we can add to this to build a basis for the entire 5D space? And as you can see from those rows labeled U, the easiest choices are the ones that correspond to x cubed and x to the fourth.
So the polynomials that match up with those new vectors we added, x cubed and x to the fourth, they create their own subspace, which we'll call U. This is it. This is our missing piece. It's a two-dimensional space that is completely independent of anything and everything that T can possibly produce.
Okay, so now we have our two distinct pieces of the puzzle. We've got the image of T, which is the 3D space our machine can create, and we have this subspace U, the 2D space it can't. So how do these two pieces relate to the entire 5D universe of polynomials? And this is where this really powerful idea of a direct sum comes into play. It's a way of saying that a bigger space can be perfectly built from smaller, non-overlapping building blocks. It's kind of like having a set of Legos where you have exactly the right pieces to build your model. There's no overlap and there's nothing left over at the end. And this right here, this is the beautiful, elegant conclusion to our whole problem. It says that the image of T and our complementary subspace U fit together perfectly, like puzzle pieces, to reconstruct the entire 5D space. It means every single polynomial of degree 4 or less can be uniquely described as one part that came from the image and one part from U. Just perfect. So this journey has really shown us how a transformation's image defines its reach, what it can create. But there's a whole other side to the story we haven't touched. What about the inputs that T completely flattens, the ones it sends to 0? That's the concept of the kernel. But you know what? That's a story for another time. Thanks for joining us on The Explainer.